Okay, guys, so today we're going to start different operations with matrices. We're going to add, we're going to multiply, we're going to do all that good stuff. But before we do all that, let's talk about when are two matrices equal. Two matrices are equal if they are the same dimensions. What do I mean when I say they have to be the same dimensions? What do you know? Tori? Good, the same amount of rows and columns. So the two matrices have to have the same dimensions, and then they have to have the same, the elements in the same position have to be the same number. So for example, so I gave you two matrices. The first thing you want to do is you want to make sure that they have the same dimensions. And remember, the way we decide dimensions is row by columns. Row by columns. So you're going to figure out how many rows you have and how many columns you have. So I have one row, two rows, right? I have two rows, and then I have 1, 2, 3 columns. So that means this is a 2 by 3 matrix. Would this be considered a square matrix? Why no? Philip? Good, because in a square matrix, the numbers of rows and columns are the same. Right, so my first matrix is a 2 by 3. Is my second matrix also a 2 by 3? Yeah, this is also a 2 by 3. So we're the same dimensions, which is good. Now what we want to do is we want to make sure that the elements in the same position are the same. So here in my upper left, I have -2. Here in my upper left, I have -6 divided by 3. But what's -6 divided by 3? -2. Are they the same? Yeah, we need to now check all the elements. I have a 1, but then I have 7 divided by 7, which is also 1. I have 6, and then I have -12 divided by -2, which is 6. Go down to your second row. I have 3, and 12 divided by 4 is 3. -1, -8 divided by 8 is -1. 4 divided by 2 is 2. Are these matrices equal? Yes, they are. Okay, so we're going to say yes, because they are the same dimensions and corresponding elements are equal. All right, let's do a different one. What are the dimensions of the first matrix? A 1 by 3. Good. This is a 1 by 3. There's 1 row and 3 columns. What's the dimension of the second matrix? 3 by 1. Are these dimensions the same? No. So even though we have the same elements, right? Because the dimensions aren't the same, these are not equal. So we're going to say not equal, different dimensions. All right, so now let's talk about matrix addition. So we're going to say matrices with the same dimensions can be added. So what does that imply? If I say matrices with the same dimensions can be added, can matrices with different dimensions be added? No, you could only add them if they have the same dimensions. And then all you have to do is add the corresponding elements. So let's say I told you matrix A is -3, -2, 5, 6. And I tell you that matrix B is 4, 8, -7, -3. And now I'm asking you to find A plus B. Well, I have a 2 by 2 with a 2 by 2. Can I add them? Absolutely. They're the same dimension. I can absolutely add them. So what you want to do is the elements that are in the same position, those are the ones you add. So see how my -3 is top left and my 4 is top left? Those are the corresponding elements. So that's what we add. We're going to add a -3 plus 4, and that will be my first element. Then I have -2 in my top right and 8 in my top right. We're going to add those together for that second element. Now we're going bottom left. So bottom left, I have 5 and -7. I'm going to add those. And then we'll have bottom right. So bottom right, I have 6 plus -3. And then we just add. So we're going to have -3 plus 4 is 1, -2 plus 8 is 6, 5 plus a -7 is a -2, 6 plus a -3 is a +3. So matrix A plus matrix B is this new matrix. This is our answer. So now you want to be really careful because I'm dealing with a matrix. Do you see how I have like sort of those squared brackets? You don't want to put the lines because if you're putting the straight lines, what is that representing? The determinant. Good. let's say I told you matrix A has the elements -3, -2, 5, 6. And C is 4, and then below that -7, and then below that 1. And I'm asking you to find A plus C. Can we add these? Good. Why can't we add them? Philip?
Because they all aren't the same dimensions.
Excellent. So we're going to say we can add A plus C because they are different dimensions. Guys, what's an additive identity? Anybody remember? Additive identity. So an additive identity is something that gives you back what you put in. So for example, if I start off with A, and because it's the additive identity, what can I add to A for the sum to still be A? What do you add to anything for the sum to still be what the original thing was? Layla? 0. So the additive identity is 0. So now let's talk about the additive identity matrix. Kai? Raise your hands up, Kai. Yeah. So we'll call the additive identity matrix here I. And basically for I, all you want are zeros. All elements are 0. So that way, if you have a matrix A plus the additive identity, you result with the matrix A. Now, is it always a 2 by 2, the additive identity matrix? No, it's whatever dimensions we need it to be. It's just full of zeros. All right, let's talk about the additive inverse matrix. So for an additive inverse, basically what you want to do is you want to get back to 0. You need the sum to be 0. So if I have 2, what's the additive inverse of 2? We want the sum to be 0. So if I have 2, what's the additive inverse of 2? Danny? -2, right? So basically, if we wanted the additive inverse matrix, all you're going to do is take all of the opposite signs. So we have matrix A plus the negation of matrix A will give us the identity matrix, which is 0. So for example, if my matrix A is 1, 2, 3, 4, what's the inverse of matrix A? -1, -2, -3, -4. The additive inverse is always just the negation of whatever you have. All right, matrix addition is associative and commutative. All right, so commutative means the order you add doesn't matter. So if I have A plus B, it's the same as B plus A. It doesn't matter which one comes first, right? 5 plus 6 is the same as 6 plus 5. And the same goes for matrices. If you say A plus B, that's the same as B plus A. Right, now for associative, let's say we have more than two matrices. I have A plus B plus C. Now this deals with parentheses, because remember in PEMDAS, don't you always perform the parentheses first, whatever's within the parentheses first? So this is saying if I group A plus B together and take that sum and add it to C, it is perfectly fine and it's the same exact thing if I first grouped B plus C together and added that sum to A. It's all the same. So essentially all this is saying is the order you add matrices does not matter. It will all come out the same. All right, so we talked about addition. Now let's talk about multiplication. Okay, so there's different forms of matrix multiplication. The first one we're going to talk about is a scalar and a matrix. So what would that look like? If I said find K times A, if K is equal to -3 and A is equal to -1 to -3, and then the second column is 13, second row, 13, -5, 4. So this real number, this is called the scalar. So it's not a matrix times a matrix. It's a scalar, which is just a single real number times a matrix. So they're saying take -3 and multiply it by -1 to -3, 13, -5, 4. So all you're going to do with the scalar is distribute it into every element within the matrix. So when you distribute it in, you're going to get +3, -6, +9, -39, +15, -12. Okay, so now I think up until this point, things were pretty basic. You can add in any order as long as it's the same dimensions. If you multiply some scalar by a matrix, all you do is distribute in that scalar. Now we're going to bring it to a matrix times another matrix, and this is where things get complicated because it's not following the rules of real numbers. For example, if I multiply any real number times another real number, it is associative and commutative, right? The way I multiply doesn't matter. For multiplication, for matrix multiplication, it absolutely matters. And in order to be able to multiply two matrices, there's a very specific rule that needs to be followed. So let's talk about it. Product of two matrices. You can multiply two matrices if the number of columns in A is equal to the number of rows in B. And I'm going to put a star and I'm going to write the order you multiply does matter. Highlight that. All right, what do I mean when I say the order you multiply matters? What I mean is if in one scenario, I might be able to multiply A times B, but then I won't be able to multiply in a somewhat different order or different groupings. You'll see, I'll show you when we get there. So I want us to multiply if A is 1, 2, 3, 4, and matrix B is 5, 6, 7, 8. Okay, the first thing we want to do is make sure that we're able to multiply these. So I look at my first matrix and I realize I'm a 2 by 2. In the second matrix, I'm also a 2 by 2. So what you want to make sure of is you want to make sure of the columns in the first one, so that second number, is the same as the rows in the second one. So that second number in the dimensions has to match with the first number in the second dimensions. 2 and 2, is that the same? And do you see how there's still two factors that we haven't really considered, the first two and that last two? That tells us the dimensions of the resulting matrix. So the product matrix will be a 2 by 2. And that came from those highlighted blue numbers. All right, so how do we multiply? Let me rewrite this. All All right, so we are going to take my first row and multiply it by the first column. So the row in the first one times the column in the second one. What do I mean? So I'm going to have my first element with the first element, so 1 times 5 plus 2 times 7. That's all just for my first element. So the first with the first, the second with the second, and you add those products. Then what I'm going to do is I'm going to do the first with the second row, the second column, sorry. And in this one, I'm going to have a 1 times 6 plus a 2 times 8. That's going to get me the first element in my second column. So I have my first element in the first column, I have my first element in the second column. Now I'm going to move down to the second row. When I move down to the second row, I'm going to now work with 3, 4. And I'm going to do the same thing with 3, 4 that I did with 1, 2. So I'm going to do 3 times 5 plus 4 times 7. And then I move on to my second column, and I'm going to do 3 times 6 plus 4 times 8. And now we simplify. So 1 times 5 is 5, plus 14 is going to be 19. 1 times 6 is 6, 2 times 8 is 16, 6 plus 16 is 22. 3 times 5 is 15, 4 times 7 is 28, 15 plus 28 is 43. 3 times 6 is 18, 4 times 8 is 32, 18 plus 32 is 50. So this is the product of A times B. All right, let's do ones that aren't the same dimension. So this was a 2 by 2. Now let's do a different one. I'm going to say if A is equal, and now I'm going to have a 2 by 3. -1, 2, -6, 3, -1, 4. And then I'm going to have a 3 by 2. So we have -6, -2, 1, 4, 3, -4. I went columns this time when I was numbering them. Right, remember, a dimension is rows by columns. So I have 1, 2 rows and 1, 2, 3 columns. And in the next one, I have 1, 2, 3 rows by 2 columns. Now, in order to be able to multiply, remember, we want to make sure that the columns in the first one is the same number as the amount of rows in the second one. Does this work out for us? Yeah. What do we do with those numbers left over? What does that represent, the 2 and the 2? Tori? Good. So the product matrix will be a 2 by 2. So let's multiply. So if we're looking at A times B, we are going to have, I'm going to just rewrite it, -1, 2, -6, 3, -1, 4. First row is -6, 4. Second row is -2, 3. Third row is 1, -4. So now remember, I'm going to multiply my first row by my first column. And this sometimes helps when I know my result matrix, my product matrix is going to be a 2 by 2. I just sort of make slashes there so I know those are the only places I need to fill. I know I'm only going to have a 2 by 2. All right, so what am I going to do? In my first element, my top left element, I'm going to multiply -1 times a -6, which is a +6, plus 2 times -2, which is a -4, plus -6 times 1, which is a -6. Now I'm going to go on to that first spot in my second column. So now I'm going to do the same thing all over again. -1 times 4 is a -4. 2 times 3 is +6. -6 times a -4 is a +24. So I filled in my first row of my product matrix. Now I have to go to my second row. When I go down to my second row, I go down to my second row in A. And we're going to do that same thing all over again. 3 times -6 is a -18. -1 times a -2 is a +2. 4 times 1 is 4. Now we do that same thing with our second column. So 3 times 4 is 12. -1 times 3 is a -3. 4 times -4 is a -16. So the product of A times B, matrix A times matrix B, is going to be -4, right? The 6's cancel. And then we'll have 26. And then we'll have a -12 and a -7. Can we multiply these two matrices? Layla?
No, because the number of rows doesn't include the number of columns.
Good. So right here, this is a 2 by 2, where this is a 3 by 2. Remember, we need the number of columns in the first one to match the number of rows in the second one. So since this is not the same, we can't multiply. All right, I'm going to give you one to try by yourself. All right, you guys do this and then we'll go over it.
So like if you download this, 32, negative 29, 30, 39.
All right, guys. Sounds like we're chatty, so we're ready. So the first thing you want to do is make sure that you can multiply. So in order to make sure that we can multiply, we're checking the dimensions. So I have 1, 2, 3 by 2, and then we have a 2 by 3. We want to make sure that these numbers are the same. Are we good to go? Yes. What is my product matrix going to be? What dimensions? My product matrix will be a 3 by 3. So it helps if you sort of set up your matrix and know it's going to be a 1, 2, 3. I need to make this bigger. 1, I'll make my numbers bigger. So there is my 3 by 3 matrix, product matrix. All right. Let's just go through the answer first. All right, somebody read me your elements by rows. So first row, second row, third row. All right.
32, negative 29, 30, 39, negative 24, 51, negative 61, 46, and negative 69.
I got the same. Who needs to see me do this? All right, let's do it. Okay, so go back here. I'm going to multiply my first row by my first column. So we're going to have negative 1 times 3 is a negative 3. Negative 5 times a negative 7 is a positive 35. Now I'm going to go on to this. Negative 1 times negative 1 is 1. Negative 5 times 6 is negative 30. Then we're going to move on to this column. Negative 1 times 5 is a negative 5. Negative 5 times negative 7 is a positive 35. Now I move on to my second row here, and I'm going to do the same thing all over again. 6 times 3 is 18. Negative 3 times negative 7 is a positive 21. Then I have 6 times negative 1 is a negative 6. Negative 3 times positive 6 is a negative 18. Move on to my third row, my third column. 6 times 5 is 30. Negative 3 times negative 7 is a positive 21. Now we go on to this third row and do the same thing all over again. Negative 4 times 3 is a negative 12. 7 times a negative 7 is a negative 49. Negative 4 times negative 1 is a positive 4. Positive 7 times a positive 6 is a positive 42. Negative 4 times 5 is negative 20. 7 times a negative 7 is a negative 49. And now you just add in each element. Negative 3 plus 5, 35, is a positive 32. 1 plus a negative 30 is a negative 29. Negative 5 plus 35 is a positive 30. 18 plus 21 is 39. Negative 6 minus 18 is a negative 24. 30 plus 21 is 51. Negative 12 minus 49 is a negative 61. 4 plus 42 is a 46. And negative 20 minus 49 is a negative 69. How are we doing on time? What do we have? Like 5? Okay, we're going to stop here. I'm going to assign you some of the homework.